Okay, so we want to compute the line integral of this vector field. I've given you the vector field, and C is the union of the left half of circle of radius 1 and the line segment from 1, 2 to 0, 1. And I didn't say it, but I'm going to give this counterclockwise orientation. So let me just say it here. Okay, so first let's get a rough sketch for what this curve looks like. That's usually helpful, sometimes more helpful than others. Okay, so you want the left half of the circle of radius 1, so that's going to be something like this. So this is x is equal to 0, y is equal to minus 1. This point here is x is equal to 0, y is equal to 1. And then we have the line segment going from 1, 2 to 0, 1. So let's say this is 1, 2. So now this is the curve, and we want the counterclockwise orientation, meaning this. Okay, counterclockwise, easy on the circle. We know what it means, and then we just give the line segment the orientation that matches up with that. Okay, don't worry, when orientations are described, they're described in a way using common language, but the way it always makes sense. If you just draw the picture, you can figure out what the orientations are. Okay, so we want to use the fundamental theorem of line integrals. So this would be the starting point. This would be the ending point. Now we need to see, can we use the fundamental theorem of line integrals? So let's call this little h, and we'll call this function little g. The derivative of h with respect to y is equal to minus xy sine of xy. And the derivative of little g with respect to x is equal to minus yx sine of xy. Of course, those two things are equal, so the y derivative of the first component is equal to the x derivative of the second component, so we can try to find a potential because we know one exists. And we're just going to go through the standard procedure. So we're going to begin by saying f of xy is equal to the antiderivative of the first piece of the first component. So what is an antiderivative of y cosine of xy with respect to x? Well, it's just sine of xy. And if you don't believe me, just take the derivative of sine of xy. Then we add an arbitrary constant, but there's an x variable and a y variable. We're only taking the antiderivative with respect to x, so any function of y is also an arbitrary constant as far as x is concerned. So that's why we have to add in the phi of y. Okay, now we're going to use the fact that g is equal to the derivative of f with respect to y. So we know that the partial derivative of f with respect to y is equal to x. Wow, what the heck was that? X cosine xy plus 2y, but we also know that this is f, so if we just take a derivative of that with respect to y, that's also the partial derivative of f with respect to y. And when we do that, we get x cosine of xy plus phi prime of y. Okay, so in other words, this tells us that phi prime of y is equal to 2y, and so phi of y is equal to y squared plus some arbitrary constant. Okay, so let me record that up here. We know that f of xy is equal to sine of xy, sine of x times y, that is, plus y squared. At least the gradient of little f is equal to big F. We could add any constant after the plus y squared, and that would also be a potential. But we want the easiest one, which means in this case the constant is equal to 0. Okay, so now we can use the fundamental theorem of line integrals. So the integral that we want to know this is equal to f of the ending point, which is 0 minus 1 minus f of the starting point, which is 1, 2. Okay, so f of 0 comma minus 1, well, sine of 0 is 0, and y is y squared is 1, so f of 0, 1 is just 1, minus f of 1, 2. So this is going to be sine of 2 plus 4. And overall, this is minus sine of 2 plus 3. Okay, so again, this was just a relatively straightforward example using the fundamental theorem of line integrals. Notice that before we found a potential, we verified that the y derivative of h is equal to the x derivative of g. If those two things are equal, then you can find a potential. If they're not equal, you cannot find a potential.